All right, let me get this going so that it doesn't have to warm up later. All right, so last we spoke, oh good, the party can start now. Last we spoke, we had seen this glorious relation that t to the fourth is 3/4. This is under various approximations, right? In particular, gray atmosphere, Eddington approximation, LTE. That under those conditions, t to the fourth is 3/4 Tef to the fourth times the vertical optical depth plus 2/3 within an atmosphere, right? So we have this idea of, oh look, it's the top of the atmosphere, the mythical top of the atmosphere where it suddenly stops, which isn't a thing, but so what? Just be sure, what would be the vertical optical depth at the top of the atmosphere? So we're looking, we're way off in space somewhere maybe, but maybe there's our eye. There's our lovely eye. We're looking into the star. Ow, ow, ow. What's the optical depth at the top of the atmosphere? It's 0 where we are. You say it's 0 where you are. You move away, you move away. What is it at the top of the atmosphere? What's the optical depth at the top of the atmosphere? It's still 0. It's still 0 because there hasn't been anything, there's nothing between the top of the atmosphere and you to absorb any light. The opacity, right? Kappa is 0 between you and the top of the atmosphere. D tau is minus kappa lambda rho ds. So wherever kappa lambda is 0, or if you do the Rosslyn mean, wherever kappa bar is 0, you're not changing the optical depth. And so tau vertical is equal to 0 at the top of the atmosphere, right? And then every different layer has both some physical depth below the top of the atmosphere, but it also has the optical depth, which is scaled by kappa rho. And so this equation is saying that t to the fourth is 3/4 Tef to the fourth, tau v plus 2/3, right? And so at tau v is equal to 2/3, we find that t to the fourth is 3/4 Tef to the fourth times tau v plus 2/3 becomes 2/3 plus 2/3, right? We're putting in tau v equals 2/3. Simplify. What is t to the fourth, right? So t, this is t as a function of tau v. So in other words, it's telling us what is the temperature at different depths within the atmosphere as expressed by the optical depth, So this is t as a function of tau sub v, plug in tau v equals 2/3, and t to the fourth is 3/4 Tef to the fourth, 2/3 plus 2/3. Simplify that expression. Yeah, just Tef to the fourth, right? Because 2/3 plus 2/3 is 4/3 times 3/4 is 1. So t to the fourth equals Tef to the fourth at tau v equals 2/3. So this is saying that if this, let's just say this is where tau v is equal to 2/3, T right there is equal to Tef. The temperature is equal to Tef at the layer where tau v, the vertical optical depth, is equal to 2/3. Does that make sense? Make sense? Not make sense? I'm seeing a lack of, yeah, question.
Last time we said that we see to the optical depth of 2/3. I don't understand that.
We'll keep talking about that. Yep. So what does it mean to say we see to an optical depth of 2/3? Yeah. Okay. Hold that thought. We'll get there. But right now I want you to buy what I'm selling here, that what this equation says is that the layer that's at an optical depth of 2/3, its actual temperature, if you assume LTE, right? We're assuming LTE so we can talk about a good approximation to temperature. If you're close to thermodynamic equilibrium, temperature makes sense. So the layer which is at an optical depth of 2/3 below the surface, if kappa and rho are constant, then remember that the optical depth is just kappa rho times the physical depth, except that the optical, you have a minus sign in terms of which way they increase, right? So in other words, well, I shouldn't say that. Yeah, we've got the physical depth below the atmosphere, right? Physical depth, like how far you actually are in meters. Physical depth in meters. And if kappa bar rho, because we're using the Eddington approximation here, gray atmosphere, if kappa bar rho equals constant, then tau v, the vertical optical depth, is just kappa bar rho times the physical depth. It's just a scale of the physical depth. If kappa bar rho isn't constant, then there's not a simple linear relationship between physical depth and optical depth. And Kathleen, this says physical, right there. Now, physical depth is what that says. This is kappa bar rho right there. Yeah. This is tau sub v. Yeah.
Physical depth
in meters. In meters. Physical depth in meters, like it's an actual distance, in other words. Physical depth in meters. So there's this layer that is at a vertical optical depth of 2/3. The temperature of that layer is equal to TEF, the effective temperature of the surface. How do we define TEF? What's the defining relation for TEF? It's that the flux we receive, what are the units of flux?
Watts per square meter.
Watts per square meter, right? The flux we receive, the watts per square meter that we receive from the surface of the star is, by definition, sigma times, what do I put in for the TEF piece of this? Sigma, yeah, sigma TEF to the fourth. That's the definition of TEF, the effective temperature. If we had perfect thermodynamic equilibrium, the star was a black body, the flux would equal sigma T to the fourth, where T was the temperature of the star. But the star is not in perfect thermal equilibrium. If it were, it'd all be at the same temperature. Temperature varies with position in the star. It gets hotter the lower you go. So, and do we see just one little thin, microscopically thin layer of the star? No, it's a fuzzball. So we're seeing light from different layers making it up to us. The further the layer is below the surface, the less of the light from that layer makes it up to us unhindered. In other words, the further you are down below the surface, the fewer photons from that layer make it all the way out without interacting in between. And so we see light when we're looking at a star, because it's a fuzzball, we see light from many different layers. Are we seeing light from the core of the star directly? No, it's way too far down. If for the sun, do you remember, I've said it before, how thick is the sun's photosphere, the layer where we get the light? It's about how many kilometers thick, roughly speaking?
400.
About 400 kilometers thick, yeah. Photosphere is about 400 kilometers thick. So most of the light we receive from most of the photons scatter in that layer that's about 400 kilometers thick. 1,000 kilometers below the surface, those photons have almost no chance of getting out to the surface without bouncing into something else first. But if you're in the photosphere, that top 400 kilometers, there's a good chance for a photon that scatters in that layer to make it all the way out into space without interacting with anything else. And the vast majority of visible light photons we get from the sun last scatter in the photosphere. That's the kind of layer that we can see. But it's not all at one temperature. It's getting hotter the lower you go. And so in general, we have to talk about TEF. We're seeing light from multiple layers at different temperatures, but we can assign an effective temperature to the radiation by saying the flux we see, while it is a blend of radiation from layers at different temperatures, the flux we see, we say is equal to sigma TEF to the 4th power, a sort of average effective temperature of the layers that we can see. And the point of that relation right there is that the actual temperature of the layer at a depth of tau V equals 2/3 is equal to the effective temperature, such that if the whole star were at the same temperature as that layer, we'd see the same flux from it. We would see the same flux that we actually do. But above that layer, is T higher or lower than TEF? Above tau V equals 2/3, is the temperature higher or lower than TEF? Lower, because higher up is lower. The temperature gets higher as you go deeper down. So here, up here, tau is less than TEF. Below tau V equals 2/3, T is less than TEF above it, T is greater than TEF below it, TE is equal to TEF at that layer. Again, gray atmosphere, Eddington approximation, local thermodynamic equilibrium. These are all approximate relations, but they're useful even when the assumptions don't fully hold. It's still a useful way to think of things. So we're really getting a blend of layers above tau V equals 2/3, where the temperature is less than TEF. We're getting radiation, not as much because it's further down, from layers that have T greater than TEF. Blend all that together, and it has the same flux as what you would get if the whole star was at a temperature of the layer at TV equals 2/3. That's the layer where the actual temperature is equal to the effective temperature. Okay, that's the content of that statement. Does that make sense? That's what we're getting at here. That's the significance. Okay, so what questions do you have? What doesn't make sense in all that? So what does it mean, is a question, when we say we see to an optical depth of 2/3. It means exactly that. In other words, we don't literally see to an optical depth of 2/3. We don't see anything above that. We don't see anything below that. All we see is the stuff at an optical depth of 2/3. No. We see some light from above that. We see some light from below that. The point is, when we say it's sloppy language, it's really code for a more precise statement. Sloppy language, we see to an optical depth of 2/3. Is code for, right? It's like, you know, we're the people that know. What's the word, cognoscenti or something like that? The people that know something, right? Wink amongst ourselves. We know what this really means, right? Is code for the blend of radiation from the star's surface layers double quotes, looks like the radiation coming from the layer at tau v equals 2/3. Even that's a little bit sloppy, because what we mean is the flux is the same. The flux is the same as it would be if the whole star were at that temperature. So I'll be more, looks like the radiation, okay, I'll say it like this. Coming from the layer at tau v equals 2/3. More precisely, T equals TEF for, in this layer. That's really what it means. The actual temperature is equal to the effective temperature in that layer at tau v equals 2/3. So the star kind of, you know, in terms of the flux we're getting from it, it's as though the star were all at that temperature. And we can get a lot of mileage out of that. So need to set my laptop not to log out on me when that happens, or at least go sleepy. Okay, so for example, there's a very important phenomenon called limb darkening. And we can use our understanding of this concept to get an understanding of how limb darkening works. So, limb darkening refers to boats on a shore. No, it's not. Limb darkening. Here is a photo of the sun. And I don't know how well you can see it from the photo, but if you look carefully, and let me get our audience at home able to see this here. If you look carefully at a photo of the sun, you may notice that it's a bit brighter at disk center than it is on the edges. The edges look a bit dimmer than the center of the disk does. And astronomers call the edge of a disk, of the apparent disk of a celestial object, they call that the limb, same spelling as your limbs, right, arms and legs. So we talk about limb darkening, where the edge of a star appears darker than the center does. Now, for the sun, we can actually observe it. Other stars look like pinpoints, but they still exhibit it. And if, for example, you're interested in studying, I don't know, star spots, and you're trying to model their effect on the star's brightness, you need to account for the limb darkening in order to properly model the brightness variations of the star due to the star spots. Here's star spots on the sun, regions of strong magnetic activity that suppress convection, which is the major way that heat is transported in the sun's outer layers. More on that later, but they cool down and become darker than the rest of the surface. On the sun, we call star spots sunspots. So sunspots are solar star spots. In any case, how can we understand limb darkening? Here's a figure from your book. Let's think in terms of this idea that we, quote unquote, see to an optical depth of 2/3, okay? And so here is the sun. It's really a sphere sticking into and out of the page. And here's Earth way off this way, line of sight towards the star's center. And the idea is that if you look towards the limb, there's an angle between your line of sight and the surface, right? Your line of sight's at an angle to the surface. And whatever line of sight we're talking about, the radiation looks like the radiation coming from the layer in this sense, T equals TEF for that layer, looks like the radiation coming from the layer at an optical depth of 2/3. And that's going to be roughly the same distance along the line of sight, no matter which line of sight you're looking at, but how far below the surface that is differs depending on whether you're looking at disk center or towards the limb. Because if we have a line of sight towards the star's center, you're looking straight down into the star. So here's the layer where the vertical optical depth is 2/3. Now this is greatly exaggerated. Tau equals 2/3 on the sun is, more like 400 kilometers or thereabouts, right? Which is a tiny fraction of the sun's radius. I think I've said it before. If you draw a picture of the sun with a pencil, or draw a circle to be the sun, the line you drew is way thicker than the photosphere is compared to the real sun, which is why the sun appears to have a sharply defined surface, even though it's a cute it's a cute giant fuzzball, right? So here, this is the layer with again, exaggerated how far down it goes. Here's the layer with a vertical optical depth of 2/3, but now, even though, what I was saying, no, I don't want to say that, okay? But now, we look along this other line of sight, we still see along that line of sight to an optical depth of 2/3 along the line of sight, about the same distance you penetrate into the solar material or the stellar material to get down to an optical depth of 2/3 along the line of sight. But that's at a level that is higher than a vertical optical depth of 2/3. We only get down to this layer, which is further out than a vertical optical depth of 2/3. And so an optical depth of 2/3 along the line of sight, which I should say in general, right, we said before, oh, you see to a vertical optical depth of 2/3. Really, I should say, in general, we see to an optical depth of 2/3 along the line of sight, not just vertically, but along the line of sight, we see to an optical depth of 2/3. That's higher up in the atmosphere because of this slant effect, right? Notice this distance that we see into the atmosphere, the physical distance is the same in either case, essentially. But because of the line of sight being a slant, we're seeing a higher layer near the limb. We're seeing down to a higher layer near the limb than we are at disk center. And what's true about this temperature of this higher layer compared to the layer that is a vertical optical depth of 2/3, this layer that is a slant optical depth of 2/3, what's true about its temperature compared to the layer at a vertical optical depth of 2/3?
Lesser?
It's lesser, yeah. This layer is higher in the atmosphere and cooler, so when we look towards the limb, we're seeing higher, cooler layers of the star than when we look towards the center, and cooler means darker, means less bright. So the limb looks less bright because along the slanted lines of sight that we have when we're looking towards the limb, we're seeing higher, cooler layers than we do towards the center. And so as a result of that, we see limb darkening. What questions do you have? Because just asking me to, like, ask a question like that on the final, like, explain how limb darkening works, referring to this picture, something like that. So that means you're going to ask me right now if you're not sure how you would do that. You look like you might have a question. You might, okay? Okay, keep thinking about it, okay? Meanwhile, oh, look, there's a theta right there. And remember, we've had lots of cosine thetas and secant thetas and so forth showing up. What do we call the cosine of theta? What symbol have we used for the cosine of theta in here? The cosine of the, yes, mu, right? So limb darkening models usually are a function of mu, which is the cosine of this angle to the vertical to the surface. And the reason that shows up is because to first order, remember that the vertical optical depth and the slant optical depth are related to the secant of theta, or 1 over the cosine of theta. So in other words, mu is showing up in considerations like that famous mu that we love so much. And I forget what the next one is. Yeah, we don't do that one. Okay. Well, no, we do that one. Okay, but has everybody had your fill of this figure yet? So now I want to talk about spectral lines, right? So stars, do they show typically an emission line spectrum or an absorption line spectrum? If you take the spectrum of the sun, is it an emission line spectrum or an absorption line spectrum?
Absorption.
Well, it's definitely an absorption line spectrum. It's an absorption line spectrum. It's, why, here's the sun spectrum right here, spread out into many, many, many strips, right? You know, this is like a very high resolution spectrum. You snip, 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 and just lay it out instead of along a single line like this. Crossed by all these dark lines, right? Fraunhofer lines, they're called, because they were discovered by Josef Fraunhofer back in, I think it was like 1814 or 17. I don't remember when it was, but anyway. So there are multiple kind of, have you ever seen sometimes on YouTube, there'll be these videos where like there's one that's like general relativity explained to different levels, and it's like for a 5-year-old, right? And for a 3rd grader, and for a, right? Okay. So there's various levels of explanation of why stars have an absorption line spectrum. And so first I will tell you the Astronomy 111 level explanation, and then I will tell you the Astronomy 310 level explanation of why stars have absorption lines. So the Astronomy 111 level explanation is to think in terms of what astronomers call a quote-unquote reversing layer, so to speak. So deep down in the star, you've got hot, dense gas. And if you have a hot, dense gas, does it produce a continuous, essentially black body spectrum? Does it produce an emission line spectrum? Does it produce an absorption line spectrum? In the limit that you've got a optically thick gas, and there's a homework problem where you will show this. If you have an optically thick gas, you cannot see through it. Do you know? Do you get a continuous rainbow spectrum? Do you get absorption lines? Do you get emission lines? What is it? What is it? What is it?
Emission?
No. Nice try, though. That's if you have an optically thin hot gas that you can see through. For example, an interstellar cloud like the Orion Nebula has an emission spectrum. A spectral tube has an emission line spectrum. It's optically thin. The atoms in it emit specific wavelengths. It's optically thin. Why? I'll bet there's a homework problem where you show that if the gas is optically thin and hot, you'll get an emission line spectrum. But if it's optically thick, then what? It's a continuous spectrum. It's a continuous spectrum. If it's optically thick, photons have plenty of distance over which to thermalize before they escape from the gas, and things come into essentially thermal equilibrium, and you get a continuous spectrum. So the radiation coming from hot, deep layers within the sun is a continuous rainbow spectrum, but in the sun's outer layers, the photosphere, that's a cooler layer sitting above deeper layers which are producing a continuous spectrum. Well, if you have atoms that are bathed in a continuous spectrum of light coming from below, do those atoms find some of those wavelengths to be especially delicious and want to absorb them? Yes, they do, right? In other words, if you're a hydrogen atom, let's say that you happen to be in the n equals 2 level. Maybe somebody bumped into you and put you into the n equals 2 level. Why, you might absorb some photon. You might absorb a photon as a result of that. Why, you might jump from n equals 2 to n equals 3. Anybody remember that? So that's what spectral series starts in n equals 2? Oh, please, please, no, please, no. The Balmer series, yes, yes. The Balmer series, and n equals 2 to n equals 3. Do you remember what color is that spectral line? Oh, it's a deep, beautiful red line. It's a ruby red, beautiful ruby red line. And if you jump from n equals 2 to n equals 4, it's a beautiful maybe t or teal, or maybe aquamarine. It's a lovely blue-green color. And if you jump from n equals 2 to n equals 5, or n equals 2 to n equals 6, then you're a jerk, because then you're absorbing a photon that could arguably be called what? Maybe. I mean, yeah, you're a good person, because you're not saying indigo. Yeah, so those are the Balmer series spectral lines, right? So stars show Balmer series spectral lines. You know, what kind of temperature gives you good, strong Balmer lines? Please, 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 please. About what temperature? About 10,000 Kelvin, right? Because that's when you get as many of the hydrogen as a fraction in n equals 2 as possible. Still tiny. Still only like 1 out of every 100,000 hydrogen atoms will be in n equals 2, even at best. But it's better than at lower and higher temperatures. So the astronomy 111 level explanation is that, where do the Balmer lines come from? Hydrogen atoms at the top of the sun's atmosphere are absorbing Balmer series wavelengths from the hotter layers below, removing them from the spectrum, and so you see dark lines at those wavelengths. That's the astronomy 111 level explanation of why a star has absorption lines. The atoms in the cool outer layers of the star, cooler. There's nowhere in a star that's cool, right? There's nowhere in a star it's like, damn, I need a jacket. No matter where you are in a star, you're like, I'm vapor, or whatever, right? Still, relatively cool outer layers. Atoms absorb spectral line wavelengths from the light coming up from below and eliminated from this, they remove them from the spectrum, and so you see absorption lines of those wavelengths. Does that make sense? That's kind of the astronomy 111 picture. All right? Now, let's take this to the next level. I feel like I should have like these things, like, right? Let's take this to the next level and understand it in terms of, again, we're not under the conditions really of Eddington approximation, blah, blah, blah. Still, it's useful to think in terms of, and you often get away with this idea of you see to an optical depth of 2/3. Okay, so let's keep going with that. You see to an optical depth of 2/3, or at least you see to some optical depth, no matter what the assumptions are. So let's say you're seeing to an optical depth of 2/3. So let's make a plot and imagine that we're looking at a stellar atmosphere. And this will be kind of the more qualitative version that you'll make more mathematically precise in a pair of glorious homework problems, the last two of them. I love those two problems, and you will have no choice but to love them as well. So, I mean, after all, you're going to joyfully show that if you have an optically thin gas that's hot, you'll see emission lines. But if it's optically thick and you've got a source of light behind it, you'll see absorption lines. So we'll talk kind of the qualitative picture of that. So here we are. It's a star, stellar atmosphere. Top of atmosphere. Okay. And up here, let's make a plot of opacity versus wavelength. Kappa lambda, the absorption coefficient versus wavelength. I guess the best axes are straight lines, so let's make one of those. Well, sort of, okay. All right. So, in general terms, kappa lambda overall tends to be smoothly varying with wavelength, and that's what we call continuum opacity. It's just kind of smoothly varying with wavelength, except at certain wavelengths, it suddenly jumps, right? So I will scan across wavelength. I will untie my shoes by accident. I will scan across wavelength here. Whoop! I'm the opacity. Hi, I'm the opacity. I am really trying to untie my shoes and, yeah, okay. What wavelengths am I jumping at? Not specifically, I'm not saying 437, no, I mean like in general, what makes the opacity jump suddenly? Properties of atoms that make the opacity jump suddenly. Like for example, so, yeah.
Just like energy levels of the...
Yeah, so suppose here I am near the Balmer alpha wavelength, the one that corresponds to hydrogens going from n equals 2 to n equals 3. And the opacity is basically how hard it is for a photon to get through unscathed, traveling through the gas, if you will, right? That's what opacity represents. Because photons, they just want to mind their own business, but they're surrounded by gas that wants to absorb and scatter it. So at the Balmer alpha wavelength, the opacity jumps. Why did it jump? Why is it harder for a photon to get through the gas at the Balmer alpha wavelength?
It got eaten up.
It gets eaten up. Yeah, there's a higher chance that it'll get eaten up. In terms of, right, at that wavelength, really a little narrow spread around it because spectral lines are never 100% sharp. At that wavelength, the hydrogen atoms are just like hungry, right? Any hydrogen atom in n equals 2 is like, gimme, right? If you're at that wavelength. So if you're not at that wavelength, you know, it's like, ha, 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 ha. Oh, whoops, there's a free electron I got pumped. But whatever, right, for the most part. But if you're at the Balmer alpha wavelength, you're surrounded by hydrogen atoms that want to eat you. And so you don't get as far. Or in other words, the opacity jumps right at spectral line wavelengths. Every time there's a wavelength that there's atoms around that can absorb that because it's one of their spectral line wavelengths, the opacity jumps. So if I make a plot of opacity versus wavelength, it's something like usually nice and smooth, but wee, not all the bumps are the same because some absorption lines are stronger than others because it's also related to how many types, how many of the atoms are present and all that sort of thing, right? In the right energy level, no sneezing, etc. So anyway, you get all these jumps in the opacity at spectral line wavelengths. Spectral line lambdas are where kappa lambda spikes up. Boom. Spectral line lambdas are where kappa lambda spikes up. So, if we follow along here, well, now we can imagine that if the atmosphere were gray, remember, what's a gray atmosphere? That's one where the opacity depends how on wavelength. It doesn't depend. So if it was a gray atmosphere, meaning kappa didn't depend on wavelength, you'd see to the same depth at every wavelength within the star, right? Because the optical depth would be, the optical depth tau equals 2/3 would be the same at every wavelength in a gray atmosphere. Even if it's not a gray atmosphere, kappa lambda is varying smoothly, so there's just a gradual change with wavelength for the most part of where the tau equals 2/3 level is. So I'll make kind of qualitatively here something like this, like maybe this is tau lambda equals 2/3 for continuum opacity, for continuum, meaning smoothly varying. So we'd be looking down about the same depth. If it's a truly gray atmosphere, it'd be exactly the same depth everywhere. I'm allowing for it. Yeah, well, opacity does depend on wavelength. So you'll see deeper at some wavelengths, less deeply at others. But still, if we're in a relatively narrow range of wavelengths, it's about the same for all of them. So there's tau lambda equals 2/3. Really, I'll say tau lambda vertical. So I'm letting it depend on wavelength. Tau lambda vertical is 2/3 for continuum smoothly varying opacity. What would the star look like if that were the case? If the opacity is smoothly varying, would we see spectral lines or would we see a continuous spectrum from the star? We're seeing about the same depth and therefore to about the same temperature everywhere. So what will we see? Do we see spectral lines or more of a continuum? Continuum in that case. We see a continuum. But what happens when the opacity jumps so that photons have more trouble making it through the atmosphere? Does tau lambda equals 2/3 occur higher up in the atmosphere or deeper down in the atmosphere at wavelengths where kappa lambda is large? Yeah, if I don't say, it's like, let me reconsider, right? Yeah. Right, so remember that the optical depth is, well, at any given wavelength, assuming kappa lambda doesn't depend on position within the star, now rho is changing, is roughly, this is cheating, kappa lambda rho times physical depth. Now, the problem is rho is changing with depth, okay? So roughly, right? So in other words, the more opaque the material, the larger is the optical depth at a given location below the surface. The optical depth gets bigger when, for a given position below the surface, the optical depth is bigger when kappa lambda is larger. And so, if I plot the tau lambda v equals 2/3 level for the actual opacity, every time there's a spectral line wavelength, it jumps to higher in the atmosphere. Well, this won't get tedious. And pretend these are actually vertical lines. They're a little tilted, leave me alone. Okay, so in other words, if we make our plot of where tau lambda v is 2/3 is, it leaps higher in the atmosphere at spectral line wavelengths. And the more absorption there is, the greater the opacity is, the higher up it leaps. So it's like wee, and then it doesn't leap quite as much with this one because that's not as opaque there. So you get something like this, wee, wee, wee. It makes this noise too. Wee. Right? So tau lambda v equals 2/3 is higher in the atmosphere at spectral line wavelengths. is higher up in the atmosphere at spectral line wavelengths, wavelengths that atoms are especially hungry for. So at spectral line lambdas, we see down to blank, blank layers than at continuum wavelengths. And again, continuum versus spectral line depends on the gas. It depends on what atoms are in the gas. If there's no hydrogen around, then the Balmer series wavelengths are continuum wavelengths. But if there's hydrogen around, oh, those are spectral line wavelengths. So at spectral line wavelengths, we see down to choose between higher, well, let's see, shallower, I'll say, shallower, comma, deeper, and over here, cooler, comma, hotter. Your task, pick the right things to fill in the blanks. At spectral line wavelengths, are we seeing further down or higher up into the atmosphere? Higher up, right? Higher up. We don't see as far. The atmosphere is harder to see through at those wavelengths. It's more opaque. So we see layers that are higher up, shallower in other words. They're closer to the surface. They're closer to the surface. We see to shallower, or if you prefer, higher, if you like. Take your pick how you want to think of it, as you want to think of it as higher up, shallower, you take however you like, or just think of it both ways, it's the same thing. And are those layers hotter or cooler than the ones deeper down? Cooler. We see shallower, cooler layers than at continuum wavelengths, but cooler implies, if the gas is cooler, why is it brighter or dimmer? It's dimmer, right? Cooler means dimmer. Cooler means dimmer. So the star's spectrum is dimmer at spectral line wavelengths. Is dimmer at spectral line wavelengths. In other words, why there's wavelengths where it looks dimmer than at other wavelengths where it looks brighter, and so we're seeing No, not in this case. Now, we do see limb darkening for a similar reason, but I'm talking about what D's? Oh, look, a wavelength where we're seeing shallower, cooler layers that are higher up because the gas is more opaque there because it's a spectral line wavelength. So collectively, we call all these dark lines there, why they are absorption lines. Absorption lines. That's the point. Absorption lines. Absorption lines. Yes. Woo. Absorption lines. Absorption lines. That's the Astronomy 310 understanding of why stars have absorption lines. because the stellar material is more opaque at wavelengths corresponding to spectral lines. So at those wavelengths, we see higher, cooler, darker material than we do at other wavelengths. You're seeing the higher, cooler, darker layers of the atmosphere at those wavelengths because you can't see as far into the atmosphere at those wavelengths. So you see absorption lines. So that's what's going on here. Absorption line wavelengths are ones where we can't see as far into the star, and so we see cooler, darker layers at those wavelengths. Okay? What questions do you have?
So,
Yeah.
that ultimately affects limb darkening, right? So we see less limb darkening?
Yeah, so it gets complicated, right? So limb darkening, we're really thinking there in terms of continuum light. Okay, so ignore spectral lines for a minute, right? So even if there were no spectral lines, we would still see limb darkening because we would see higher up layers towards the limb than we do towards the center. And so that would absolutely be the case. Now, if you have spectral lines, you can have a narrowband filter that will only let in the light from wavelengths near that of a single spectral line. And that can be a really powerful tool because, for example, take the Balmer alpha line, the n equals 2 to n equals 3 line. So the sun is relatively opaque there, but it does depend on wavelength. And if you have a tunable filter where you can let through a very narrow range of wavelengths, you can probe different layers of the atmosphere by moving on either side of the spectral line. The further away you are from line center, the further down you're looking, and the closer you are to line center, the higher up you're looking. And so you can actually probe different layers of the atmosphere by having a tunable narrowband filter that allows you to look to different depths of the atmosphere at different wavelengths. And in the Balmer alpha line in particular, it actually has an emission core, so to speak. In other words, its profile actually has a bump in the middle. And that's because well, we'll get to that next level thing after the break. Because we have to understand that, we have to imagine, well, what if temperature was increasing with height instead of decreasing with height? Okay, so continuing on with this idea, we're soon to move on to the structure of spectral lines because that's an important diagnostic in astrophysics. Jumping ahead a little bit, here's kind of, you know, a spectral line profile, right? So spectral lines are not perfectly sharp. It's not true that it's really one exact wavelength that would get absorbed. There's always some width to the spectral line. So there's a central wavelength where the probability of absorption is highest, but it just gradually fades towards almost zero on either side of that. So here's the basic idea of a structure of a spectral line. But in the sun, if you look very closely at the H alpha line, you find that there's a bump in the middle of it. That's that red spectral line that corresponds to the 2 to 3 or 3 to 2 transition. If you look at the sun's H alpha spectral line, plot versus wavelength, the intensity it actually looks something like this. There's a bump in the middle of it. It actually gets brighter again in the middle of it. And that is because of the sun's chromosphere, the layer above the photosphere, where temperature actually rises with height. So, you know, we've said before that temperature increases as you go deeper inside a star. And that's for the most part true, and now I'm double checking that I really turned on the camera. That's for the most part true, but in the sun, and the sun is not unique in this regard, in other cooler stars that have convective outer layers, above the photosphere, the temperature actually starts to rise with height, and so there's a layer called the chromosphere, where the temperature gets to around like 30,000 Kelvin, and then you have the corona, where the temperature goes up to more than 1,000,000 Kelvin. It can go to 2 or 3 million Kelvin. So that's a ongoing topic of research is, well, how do you manage that? There has to be some sort of work, electrical or mechanical work being done to cause the temperature to start rising with height instead of falling with height, because normally heat flows from hotter regions to cooler regions, and it wouldn't make sense otherwise that the temperature would rise with height. But the point is that in the chromosphere, where temperatures get to like 10, 30,000 Kelvin or so, the hydrogen is emitting Balmer series spectral lines. That's true everywhere. I mean, in other words, certainly hydrogen atoms in the sun's photosphere are also jumping down from n equals 3 to n equals 2 and emitting Balmer alpha. But in the chromosphere, where it's hotter, here's what happens. So here is a photo. No, I'm not. This is the wrong one. Here, I just pulled it up on the spur of the moment here. Here is a photo of the sun in visible light. So here's the photosphere. Here's what we normally see. But if you have a narrow band H-alpha filter put in front of the telescope, why, you can make an H-alpha telescope. And if you look through one, why, the sun looks red, and you see the chromosphere. So here is a photo through a telescope where you've got a filter in front of it that's really only pretty much transmitting the middle of the H-alpha spectral line. It's a very narrow band filter that only lets that red light through. How many of you, because we've got one at Perkins and we've set it up here, how many of you have looked through an H-alpha telescope before? So what's going on? How is it working? Well, here we were talking about before that because temperature increases with depth in the sun, then we see absorption lines, because at absorption line wavelengths where the opacity is higher, we're seeing to shallower, higher up, cooler layers. But what if the temperature is increasing towards you instead of increasing away from you? What if the temperature is increasing with height towards you rather than decreasing with height towards you? What would happen then? In other words, what we talked about over here before, and for the audience at home, I need to turn the camera over that away again, because it isn't right now. I've added, and maybe add this to your diagram that you made before if you were following this along, right? Temperature is increasing downward, so cooler up here, hotter down here. And the point is, when we can't see as far into the atmosphere, we're seeing cooler layers that are darker. But what if this were reversed? What if temperature was increasing upwards? Now that can't be true overall for the sun, because we need to transport energy from the hotter core to the cooler surface. Can't be true overall for the sun. But above the photosphere, where it's very tenuous, the gas is very tenuous, that actually is true, that temperature increases upwards, away from the center. What if we reverse the arrow and it was hotter up here and cooler down here? Then at spectral line wavelengths, where the gas is more opaque, we would see to higher up layers, still shallower layers at spectral line wavelengths, but instead of being they would be Instead of being cooler, they would actually be hotter, and so you would be seeing hotter, brighter layers at spectral line wavelengths instead of cooler, darker layers. So you don't see absorption lines, you see emission lines in that case. If temperature increases towards you, you'll see emission lines at spectral line wavelengths. If it increases away from you, you'll see absorption lines at spectral line wavelengths. All right, so that's one thing. Now consider the chromosphere. It's doing exactly that. Temperature is rising towards us, rising with height towards us. So when we observe a very narrow range of wavelengths at the center of the Balmer alpha line where the opacity is highest, we actually see this bump because we're seeing higher up chromospheric levels that are brighter rather than dimmer. And so the way an H-alpha telescope works is through that narrow filter, the hydrogen gas is opaque enough that we can't see all the way down to the photosphere. It has enough opacity that we don't see all the way down to the photosphere. Instead, we can only see down into the chromosphere. And hence we get this very different appearance. This is the solar chromosphere that we see at the center of the H-alpha wavelength, rather than the photosphere that we see at other wavelengths. Now, if you don't put the filter there, yeah, that light from the chromosphere is still there, but it's absolutely overwhelmed by the light from the photosphere. It's there, but you can't see it because it's like, photosphere, I can't believe it, right? But if you have that very narrow filter, then you don't see down to the photosphere, you only see into the chromosphere, and you see this layer, and it's like, ooh, you can see all these phenomena that you can't see if you have a broadband view where you're looking at a big, huge range of wavelengths. So I forget what your question was, but that's my answer to it at least. Yeah, what was your question? Do you remember?
Does the opacity affect the limb darkening?
Oh, yeah. So it would be true. Limb darkening is a function of wavelength, is what it comes down to. Because, for example, if we look through the blue filter, what we're doing is, if you look through the blue filter, you're seeing a narrow range of wavelengths, and essentially you'd be saying like, okay, well, assume that you're seeing to the same layers in the atmosphere, whether you're looking through a V filter, Verde, the visual filter, or the blue filter. The point is that if you have two objects at different temperatures and you compare the Planck spectra as a function of wavelength, there's a bigger contrast for stellar temperatures. There's a bigger contrast between the Planck function for a hotter temperature and a cooler temperature at short wavelengths than there is at longer wavelengths. And so you see more limb darkening through the B filter than you do through the V filter, because the ratio of the brightness of the blackbody spectrum at a hotter temperature to a cooler temperature between the same blue wavelength is bigger than the contrast between the same green wavelength, for example. And it's, of course, filters a whole range of wavelengths, but you do see filter-dependent limb darkening. The amount of limb darkening depends on wavelength because of the fact that if you compare Planck spectra at two different temperatures, the ratio of the brightness at a given wavelength tends to increase at shorter wavelengths compared to longer wavelengths for stellar kinds of temperatures. So I think that's the answer to your question. Yeah. For a spectral line, well, it'll get pretty complicated, is what it comes down to. But anyway, okay, so. But in general, you would expect that if you were looking at narrow band filters that are at shorter wavelengths, you'll get like spectral, if you look through a spectral line passing filter, you'll get more limb darkening at shorter spectral line wavelengths than longer spectral line wavelengths. Anyway. Okay, what questions do you have? Yes?
So if I have a telescope with the H alpha filter on it,
Mm-hmm.
it would absorb all the wavelengths I get from the photosphere and just show.
So it's not that it's absorbing the wavelengths from the photosphere. It's not that the telescope itself is doing that. It's that the hydrogen, the photons coming from the photosphere will interact in the chromosphere before they can just escape into space. So it's the chromospheric gas itself that is preventing those photospheric photons at that wavelength from getting directly to us. Instead, we're getting photons from the chromosphere at those wavelengths because we can only see down into the chromosphere at those wavelengths. It's the chromosphere that is the layer where those wavelengths last interact before coming out into space. And so we see the chromosphere at those wavelengths. Photospheric light at those wavelengths will be stopped by the hydrogen in the chromosphere for the most part before it gets out to us. So we don't see the photosphere, we see the chromosphere instead. And the chromosphere is hotter, and so you get this bump up there in the intensity. It's still darker than the rest of the surface, but it's brighter than nearby wavelengths are as a result of that. So, fun with radiation transfer. Okay. All right. Okay. I now want to see if because I want to say another thing that will be of assistance when you're doing the last two homework problems, which is, it refers to this formal solution of the transfer problem, and you're using it to mathematically show some of the kinds of things we're talking about here. To mathematically show that an optically thin gas that's hot will produce emission lines. If it's optically thick, it will produce an absorption spectrum. But if there's a hotter source of radiation behind it, then you will see, as long as it's optically thin, you will see absorption lines as a result of that. If it's optically thick, you won't see the source behind it. You'll just see the source itself. And when I say, by the way, I'm saying optically thin, optically thick. A layer of gas is optically thick if the optical depth of the back of it is much greater than 1. Right? The front surface of it is at an optical depth of 0 for you. If the back surface of that layer, if its optical depth is much more than 1, we say it's optically thick, because that means that you're not able to see through the gas. If the optical depth is much greater than 1, you're not getting any photons from back there. And so an optically thick layer is one that you cannot see through, roughly speaking, whereas an optically thin layer is one you can see through it. You might see light coming from it, it's glowing, but you could still see stuff behind it. So if we put some optically thin glowing hydrogen in front of us, there'd be this lovely pink glow everywhere, but I'd still see you all through it, is what it comes down to, if it's optically thin. If it's optically thick, it'll just have a black body spectrum. It won't have an emission line spectrum, an absorption line spectrum. It'll have a black body spectrum if it's optically thick. And you saw some hints of that. Remember when you looked at the hydrogen lamp, you saw spectral lines, but were those the only wavelengths you could see? No, you could actually see other colors as well. It's just that the emission lines were much stronger. But if you made that gas thicker and thicker, those other wavelengths would get stronger and stronger until they matched up in intensity with the emission lines, and you wouldn't see the emission lines anymore. You would just see a black body spectrum in that case. Do you remember that? Do you remember that you could see other colors than just the emission lines? Yeah, as long as it's optically thin, the emission lines will dominate. Bremsstrahlung, et cetera, is producing other stuff, other wavelengths. But if it gets optically thick and all the radiation can thermalize, it turns into a black body spectrum instead of an emission line spectrum. And you'll joyfully show that in those homework problems. Here's part of joyfully showing that in those homework problems. Formal solution of the radiation transfer equation, of the transfer equation. So here's the transfer equation, and it's been a while, so maybe you forgot. So I'll remind you. The radiation transfer equation says that d I lambda d tau lambda is I lambda minus S lambda. Where remember, S lambda is the source function. And that was J lambda over kappa lambda, if I'm recalling correctly here. I'm almost sure I'm right about that. I feel silly even having to look for this. Oh, I have to turn in my card. Where did it go? I'm going to end up just writing that. Yeah. There we go. Yeah, it's J lambda over kappa lambda, right? The emission coefficient divided by the absorption coefficient is J lambda over kappa lambda. And remember that d tau lambda is what times ds? D tau lambda is minus There's no I lambda part of it, just because this is just talking about absorption and scattering. Kappa lambda rho, yeah. D tau lambda is minus kappa lambda rho ds. So this can also be written as minus 1 over kappa lambda rho di lambda ds is I lambda minus S lambda. Or we can just say that d tau lambda is minus kappa lambda rho ds and say the derivative of the specific intensity with respect to optical depth is I lambda minus S lambda. Ooh, fun with, how many of you have taken differential equations before? Oh, do you remember integrating factors? Oh, you will after I put an integrating factor here. This will be I hope it's a reminder. I hope it is, otherwise I'm going to have a word with your prof. Okay, so multiply through by an integrating factor e to the minus tau lambda. Multiply through by the integrating factor, 2, 4, 6, 8. Boy, we want to integrate the integrating factor, e to the minus tau lambda. So we get that di lambda d tau lambda e to the minus tau lambda is equal to I'll put it like this. Minus I lambda e to the minus tau lambda is equal to minus S lambda e to the minus tau lambda. So I just multiply through by e to the minus tau lambda and take the I lambda e to the minus tau lambda over to the other side with a minus sign. So that's all I've done. I just take this equation, multiply by e to the minus tau lambda on both sides, and pull the I lambda term over onto the left. Why did I do that? Because this side is now a derivative. Does this look familiar at all? You multiply through it by an integrating factor in order to turn one side of the equation into a derivative. So this side is the derivative of I lambda e to the minus tau lambda. So we can say that d tau lambda of I lambda e to the minus tau lambda is equal to minus S lambda e to the minus tau lambda. Right, because if I take the derivative, whoops, e to the minus tau lambda, not e to the minus lambda, that made no sense. if I take the derivative with respect to tau lambda of I lambda e to the minus tau lambda, well, what does the product rule tell me? Derivative of the first times the second, di lambda d tau lambda e to the minus tau lambda, plus the first times the derivative of the second. I lambda times the derivative of e to the minus tau lambda. What is the derivative of e to the minus tau lambda with respect to tau lambda? Minus e to the minus tau lambda. There's not even a tau lambda in front, just minus e to the minus tau lambda. So in other words, this is this. They're the same. They're the same. So I recognize the left-hand side as the derivative of I lambda e to the minus tau lambda. That's why you use an integrating factor to turn one side into a derivative, into a simple derivative. Okay? So now, then what I can do is multiply, right, in an example of my calculus professor, my first calculus professor, what he would call bad algebra but good calculus, multiply through by d tau lambda, so that we get the differential of the quantity I lambda e to the minus tau lambda is equal to minus s lambda e to the minus tau lambda d tau lambda. So now it's been separated. We have independent differentials, if you will, on both sides. So we integrate both sides between appropriate limits. So if we think of, again, we're like, looking through an atmosphere, for example, then we'll say that up here is tau lambda is equal to 0, and I lambda is whatever its value is for tau lambda equals 0. So it's I lambda is the value where tau lambda is equal to 0. And down here, tau lambda is equal to tau lambda naught, we'll call it. So tau lambda of the starting point of the radiation, the source of the radiation, if you like, is tau lambda naught. And I lambda at this starting point, we'll call that I lambda naught. And so we integrate between corresponding limits on the two sides. So in other words, we integrate from e to the minus tau lambda naught I lambda naught, because over here this is a differential of I lambda e to the minus tau lambda. So at the location where tau lambda is tau lambda naught and I lambda, we're assigning to have a value I lambda naught at that location, that'll be our lower limit. Right, because down here, in other words, down here where tau lambda and I lambda have these two values, then I lambda e to the minus tau lambda at that location is e to the minus tau lambda I lambda naught. Does that make sense or not make sense? So that's my lower limit. That's my lower limit, because this is saying, right, I'll just be very explicit, if these are the values of tau lambda and I lambda, then automatically I lambda e to the minus tau lambda at that location, by our definition here, is I lambda naught e to the minus tau lambda naught. So that's my lower limit. That's my starting point. On the left-hand side, this is going to be d e to the minus tau lambda I lambda. I'll put it in the same way I did of d I lambda e to the minus tau lambda, not that it made any difference. E to the minus tau lambda over there. So what's my upper limit over here? What is I lambda e to the minus tau lambda up here? Yeah, here, I lambda e to the minus tau lambda is I lambda of tau equals 0, e to the minus 0. What's e to the minus 0? 1, right? Because anything to the power of 0 is 1. So this is just I lambda of 0 up here. So my upper limit is I lambda of tau equals 0. And on the right, and let me make sure, I probably have to zoom out a little bit for the audience at home who's excitedly watching all this. Go over here just a little bit. Okay, I'll just move over a little bit. Okay, so now, on the right, we've got minus the integral, and I'm not going to assume S lambda is constant. I'm going to assume that it could vary with optical depth, and I'm going to make this not be a big blue thing. If I figure it out, where's the magic button? Where is it? AV mute. Okay. So we'll have the integral of S lambda e to the minus tau lambda d tau lambda. And what are my limits? Now I'm integrating tau lambda. So my starting point, what's tau lambda at my starting point? What's tau lambda at the starting point? Did I happen to like bounce over it at any point? It's tau lambda naught at the starting point. Right? Important mathematical tool, right? The emphasis here is if you're doing definite integrals on both sides, the limits correspond to one another, right? So the lower limit is where tau lambda is equal to tau lambda naught, I lambda is I lambda naught. If I'm only integrating d tau lambda, then I only have to worry about tau lambda naught. And then up here, what's the value of tau lambda? What is it up here? It's 0. Yeah, we're integrating to the top of the atmosphere, or at least to where you are. It doesn't even have to be the top of it could just be where you are. Okay? So I'm integrating those two things there. And so these are two very simple integrals. Well, I shouldn't say that. This one you just have to keep as an integral, but this is a very simple integral, right? In other words, what is for this one, what's the integral of di lambda e to the minus tau lambda? It's kind of like saying, if I do this integral right here, what is the integral of dx? X, right? What's the integral of I lambda e to the minus tau lambda? I lambda e to the minus tau lambda. So, I mean, in my notes, I just write the answer down, but let's just be very explicit here. So this is I lambda e to the minus tau lambda evaluated between I lambda of 0 and e to the, I'll just put it in the other order, I lambda naught e to the minus tau lambda. I should have probably written it in this order here too, because that's the order I have it here. So not that it would make a difference, but if you want, you know, you could flip the order of those, because a times b is b times a. So this, for this side, you get this, which is what? When I evaluate, what do I get when I plug in the upper limit and the lower limit? It's
and to not that minus.
Yeah, right, it's just the usual thing, right? If you evaluate x between b and a, it's b minus a. If you evaluate anything between upper and lower, it's upper minus lower. So in other words, we get I lambda naught minus, I lambda of 0 minus I lambda naught. So understand this 0 means starting value, and this one means tau equals 0. It's a little confusing, but the book did it. It's their fault. I'm following what the book did. Times e to the minus tau lambda naught, the optical depth down there. That's what you get from this side, equals whatever this is. Because S lambda in general depends on tau lambda, so I can't evaluate this integral. I just say whatever this integral is. If S lambda were constant, I could pull it out, but I'm leaving it general. So, and now, ooh, minus sign. How can I get rid of the minus sign? Flip the limits, right? Equals plus integral from 0 to tau lambda naught of S lambda e to the minus tau lambda d tau lambda. Put it together and what do you got? Bippity boppity boo. This is the technical term. Oh, did I let my, let's see, yeah, there it is. Oh, isn't it beautiful? Audience at home, oh, so gorgeous. And now we zoom out a little bit so I can complete on the other side there. Oh, so beautiful. I'm going to cry. And trust me, you'll be glad we did this when we do the homework, when you're doing the homework. Because it's there in the book, but I don't know. Maybe when you're doing the homework, you're like just kind of like not gonna look, and you're just gonna try. Oh, you wouldn't want to do that. Of course, you would have looked in the derivation of the book, but now your professor is like carefully going through everything with you, you know. So because he cares so much. So in other words, we get the grand result. So grand result. We get that I lambda, where you are, tau equals 0, tau lambda equals 0, is equal to I lambda naught e to the minus tau lambda naught plus, the book has it with a minus sign because they don't flip the limits, but I'm flipping the limits, plus the integral from 0 to tau lambda naught of S lambda e to the minus tau lambda d tau lambda. This is the formal solution of the radiation transfer equation. This tells you, if you know what I lambda starts with at some particular optical depth, how the intensity varies along the beam as you move away from there. And so we can interpret these two terms. So this is saying that by the time we get to tau lambda equals 0, we don't get all of I lambda naught. It doesn't all reach us. Why not? Why doesn't all of the specific intensity I lambda naught make it up to the top? Because of the opacity, right? Because of the opacity. And this is saying, this is the attenuation of I lambda naught because of absorption and scattering in between you and the source of the radiation. So this is the initial intensity of the ray diminished by the effects of absorption and scattering. Initial intensity of Ray, and now I'm thinking of a guy named Ray. He used to be so enthusiastic, but you know, then. Anyway, the initial intensity of ray diminished by the effects of absorption. Some of the photons got lost to absorption and scattering, which we all call absorption, diminished by absorption. And dang it, I'm also going to say slash scattering, because scattering happens too. Even though we're calling scattering a form of absorption, I still think that's kind of silly. Thanks a lot, you silly fellow astronomers. The initial intensity of rays has been diminished by absorption and scattering on the way up to us. And then what this represents is S lambda e to the minus tau lambda d tau lambda, we'll put it like this. No, S lambda e to the minus tau lambda. Notice S lambda e to the minus tau lambda. Oh, look how similar that is. The idea is that here's some point where the optical depth away from us is tau lambda. S lambda represents, oh, this layer right here, it's emitting radiation towards us, but that radiation from this layer is suffering absorption on the way to the surface. And so that's what this piece represents. Radiation emitted towards us from layer at optical depth tau lambda, diminished by absorption scattering. And the integral is adding that up for all the layers between us and the initial point. The integral adds this emitted radiation up from all the layers between us and the source. You're adding it all up between us and the source. So in other words, the radiation we get is a combination of the radiation that started out that's getting attenuated on the way up to us, but there's also radiation being emitted by the gas in between us and the source, and that's what this term represents. So the radiation that began the journey in the first place gets attenuated, plus there's new radiation on the way up to us that's also being added to the beam, but the further away a given point is away from us along the beam, the less of the radiation from that point that is making it all the way to us. A greater fraction of the photons added to the beam up here make it to us than photons added to the beam down here, because photons added to the beam down here might get eaten or scattered out of the beam before they get all the way up there. But some of them can make it up. What fraction? E to the minus tau lambda of them for each of the different layers, if you will. So that's how we interpret this beast. And here is a very helpful reminder for the homework. suggestion. No, pro tip, right? That's what you do these days. Pro tip, right? Pro tip. A resource, how do you spell resources? Is it a C or a resource? Is it a C? Yeah, okay, I'll make it right. A resourceful, right? Is that right? Yeah. A resourceful astrophysics major might profit from remembering that for tau lambda much, much less than 1, well, let's put it this, remembering that, and I'll put the tau lambda much, much less than 1, that e to the minus tau lambda is equal to 2, 4, 6, 8, time to write a Taylor series, because I know you love Taylor. Stop it! Taylor series are wonderful tools. Ugh. Yay!
Dr. Harmon,
Yes.
harmonic series are much better.
You know, I love harmonic series too. I mean, you know, they just do so much for you, Amy. But yes.
If I were to choose,
Well, you know, but you know what? I love Taylor series too. They're tailor-made for some problems. I mean, they just are, right? That e to the minus tau lambda, why it's 1, what's the next term? So e to the x is 1 plus, what's the next term?
x to the,
It's x to the first over 1 factorial.
yes.
X plus x squared over 2 factorial over 2 plus x cubed over 3 factorial plus dot, 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 where the dot, dot, dots do not mean annoyance, right? I've run into this problem of I must be careful with my use of ellipsis when dealing with people younger than I am, because to me an ellipsis just means and so forth, whereas I've learned that it can also signify whatever, right? But no, this just means keep on going, okay? So if it's e to the minus tau lambda, it's 1. Yeah, plus minus tau lambda, right? Minus tau lambda. And then
Can I say plus tau lambda?
you can say that because it would be plus minus tau lambda squared, right? Which is plus tau lambda squared over 2 factorial. What's the next term? Now it's another minus, right? So it just alternates, right? Tau lambda cubed over 3 factorial plus whatever, okay? You just might want to make use of this because only the first few terms will be important when the slab is optically thick. I'm sorry, when the slab is optically thin, because then tau lambda will be much, much less than 1, right? And if tau lambda is small, tau lambda squared is very small, and tau lambda cubed is very, very small, and tau lambda to the 4th power is very, very, very small, et cetera, right? So you just might want to make some approximations that involve using this Taylor series right here. And you don't want to go too far, right? Sometimes students make the mistake of, oh, so e to the minus tau lambda is just 1 for small tau lambda. That's usually too rough an approximation. You probably at least want 2 terms, sometimes maybe 3 terms, etc. So this is good practice for the very important tool of using a Taylor series expansion to see what happens in the limit of some quantity being small. And that's why I saw Kathleen's face light up with joy when I mentioned Taylor series before. It was so inspiring to see that, yes. Yes.
It's supposed to be talent when it's done.
Of course it is, yes. Thank you. No, it's tau 3 to the lambda. Yeah.
One too many threes.
There we go, yes. Thank you.
Three is the magic number.
3 is the magic number, yes.
What was it? Schoolhouse Rock?
Oh, is it really? Oh, I guess I've forgotten about that.
369.
Oh, huh. Wow. And now let's see what some others. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Do. I think that was Electric Company maybe as opposed to Schoolhouse Rock. Conjunction, junction, what's your function? Right. Yes, and there's, what is this?
It's like the mitochondria in the powerhouse of the cell. It's like the definition.
Interjections. Hallelujah. Show emotions. Yeah. Instead of an exclamation point or by a comma when the feelings, no, not instead. Exclamation point or by a comma when the feeling's not as strong. So when you're happy, hooray, or sad, right, all that kind of stuff. Oh, or frightened, or mad, yeah, all this kind of stuff, right. And then, of course, they missed a few words, right? We the people, in order to form a more perfect union, establish justice, ensure domestic tranquility, provide for the common defense, promote the general welfare, and secure the blessings of liberty to ourselves and our posterity, to ordain and establish this Constitution for the United States of America. And I would have no idea of those words if it weren't for that song.
Nope.
Yep.
When I was in 5th grade.
But that song makes it memorable, except they just leave that, we the people of the United States, in order to, right, because that just doesn't fit as well. But, yeah, right. Yeah, okay. It's now time to go. Yes. There you go. Yes.
Now I have to find my schoolhouse.
Yeah.